Okay guys, here we go. This is again our part 2 of our segments, lines, measures, and chords notes. Okay, chapters 10.1, 10.2, and 10.3. Here's 3 chord rules that we're going to be talking about. Now the rules are given to you up top. I'm going to go through each one, talk about it, okay, then we're going to do examples of each one. Now the first thing I want to point out, guys, is these are very recognizable examples. They don't really look very similar. Here we have congruent arcs and chords. Here we have a line segment coming from the center hitting a chord at a right angle. Here it's kind of the same thing, but again you say you have 2 sets of it. So again, when you see this type of problem, when it looks like this, you're going to use this formula. Same thing here. When it looks like this, you're going to use this. Same thing here. When it looks like this, you use this. So pretty recognizable stuff, guys, okay? So I'm going to talk through each one. Congruent corresponding chords theorem. In the same circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent, okay? So what we're talking about here, guys, is if we have 2 chords, okay, that are both congruent, then that means the arcs that they intercept will also be congruent. So congruent chords will make congruent arcs. Now that goes both ways. It says if and only if. That's a biconditional. So if the arcs are the same, yes, if these are congruent, then that means these chords are automatically congruent as well, okay? So whenever we see that, that's the rule we're going to be using. Here we have a perpendicular chord bisector theorem in Converse. Again, Converse just means flip the logic, go the other way with it. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So, guys, what we're talking about here, anytime we have a line segment from the center, it says diameter here, it could also be a radius. Watch out for that. We have a line segment from the center, okay, hitting a chord at a right angle. It is automatically going to bisect that chord and bisect the arc, okay? So you see I marked these little portions of the chord. This has been cut in half. Also the arc has been cut in half. Arc measure will be divided by 2, okay? All right, so other way around, if we have a bisected chord and bisected arc, that means the line coming from the center must have hit it at a right angle. That's just going the other way with the logic, okay? So here this is a bisector problem. Line from the center hitting at a right angle, cut it in half, cut the chord in half, cut the intercepted arc in half, okay? All right, last theorem up top here, equidistant chords theorem. In the same circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center, okay? So look what we're saying here. Equidistant from the center, that's what these lines are. Now they're going to hit at a right angle, okay? So we have congruent line segments. They are the same distance from the center, so that means that line segment AB and line segment CD, okay, will be congruent if and only if they are equidistant from the center. Okay, equidistant from the center, all right? So there's our 3 theorems, guys, all right? Again, pretty recognizable. When you see one that looks like this, do this. Same thing here and here, all right? So now let's look through, let's use chords in our circles here, guys, all right? I'm going to do my best to keep this kind of folded up so we can access it quickly, all right? But again, I'm doing this at home, we're doing the best we can here, all right? So it says find the measure of the arc or chord in circle Q. Again, it's called circle Q because Q is the center of my circle over here on the right. Again, I'm going to do my best to kind of jump back and forth, get it all in view, okay? So we look here, guys, it asks us for the measure of arc WX. It asks us for line segment YZ, that would be a chord. Line segment WZ would be a chord. And the last one would be arc XY. And again, formatting it, put this little box instead of the rainbow, but that is arc XY, okay? All right, now let's look at my figure here, guys. Now, the theorem that I'm going to be using, and it kind of looks a little different, we're going to be using this first one here. And that's, again, if we're saying that the chords are the same, that means their intercepted arcs are the same. Or, other way, if the arcs are the same, then that means the chords are the same as well, okay? So just kind of follow along with me as we go through this. So once again, I'm going to set this up over here, work through my problem on the figure, then we'll just go back and give answers as we need them, okay? All right, so what we look at here, guys, as we start seeing this, first thing I see when I look at this figure is I see it gives me a 42-degree central angle right here. That means this arc out here is going to be 42 degrees. Now we also have a vertical angle here, so that means we have 42 degrees over here, which means we have 42 degrees over there. So look what we got here, guys. I have shown by vertical angles that we have congruent arcs, okay? 42 degrees up top, 42 degrees down bottom. Everybody see that? So because our arcs are the same, that means these chords are going to be the same, ZY and WX. So if WX is 3.6, that means ZY is 3.6, okay? ZY or YZ, so that'd be the answer to problem 21, 3.6. There we go. We're working through this stuff, all right? Again, the chords are the same. That means the arcs are the same, okay? Or vice versa as it was here, okay? Now, the part that kind of trips us up here, guys, that we don't see is that we have two diameters here, guys. So what this means is that these two angles are going to be the same here. Look at this. We have 42 degrees here. That means this whole angle here, WQZ, is going to be the other part of my semicircle. So again, I'm going to use 180, all right, minus 42. That's going to give me 138 degrees, all right? So I have 138 degrees here, which will be 138 degrees out here. Same thing over here, vertical angles, 138 on the inside, 138 on the outside. Does everybody see that? Okay. Now, as far as us being able to solve, it's the same situation, guys. We have congruent arc, WZ, congruent arc, XY. So that means these chords are going to be the same here too. 9.2 on this side means we have 9.2 over there. There's WZ. That's problem number 22. So again, 9.2. Because I was able to show that the arcs are congruent, that means the chords that intercept them, okay, they're also going to be the same. So 3.6 up top, 3.6 down bottom, 9.2 on the right, 9.2 on the left, okay? All right, now we've already pretty much solved for all these other pieces. So let's just go back in and fill it in, okay? Again, arc WX, we already said that that was 42 degrees here, all right? 42 degrees, there's an answer. Same thing with XY. We used a supplementary relationship because these two angles make a semicircle, 180, and that's where we got 138 degrees, okay? 138 degrees. Awesome. Okay. All right, guys. Now, last two examples here. Now, look at these two. They are very recognizable. 24 looks just like this second theorem here. Line from the center hitting at a right angle. Boom. There you go right there. Same thing down bottom. We have two chords that appear to be equidistant from the center. I'm not sure if that's exactly the case, but we'll see it, okay? Here we go. That's the third theorem here. So again, they're recognizable. Use which one looks like it, okay? All right, guys, so what we have here is we have a line from the center that hits a chord at a right angle that has automatically been bisected, okay? So this is a bisector problem. These two expressions represent either side. So when I'm solving for the value of x, we're going to do 2x minus 4.1 equals x minus 0.5, okay, or just 0.5 there, all right? Don't get tripped up by the decimals there, guys, okay? We're just going to get the x's together and combine like terms, all right? So we would solve out for x on our own there, all right? You should be able to do this one on your own. The rest of it's just algebra. Subtract x from both sides, add 4.1 to both sides, okay, and then that'll give you your answer, all right? Now, again, line from the center hitting at a right angle, it bisects the arc. That's this second theorem up top here. Last one says find the radius of the given circle. It's a little different problem here, so let's work through it. This is going to be a multi-step. Now, the theorem says is that the chords are the same if and only if they are equidistant from the center. Now we see it's telling us that both these chords are 20, so what that means is that this has to be the same measure. OY to OZ, those have to be congruent, guys. In order for those arcs to be the chords to be the same, these two line segments in here have to be the same. So we go 4x minus 5 equals x plus 4. Because we're going to have to solve for a measure here, y'all, okay? A little bit different type of a problem. Now, it asks us for the radius, but it doesn't give us a radius, okay? So what we're going to have to do is we're going to have to draw one in. I'm going to draw just OW, all right? OW is the radius I'm going to be looking for. Because what I can do here, guys, is once I solve for x, I can find the measure of OZ. I know ZW is 10 because this piece has been bisected. Same thing we just did up here. A line from the center hits at a right angle. This is 10 because the whole thing's 20. So I can use Pythagorean theorem to be able to solve for this right here, guys. Everybody see what we got going here? All right. So solve for x first. We're going to subtract x from both sides. Get my x's together. We get 3x minus 5 equals 4. We're going to add 5 to both sides. All right, so we get 3x equals 9. Divide both sides by 3. We get x equals positive 3. Okay? All right, now what we're going to end up doing here, all right, is we'll take our x value. That plugs in here. Remember, we're solving for the radius. I'm thinking ahead. So if I can find this measure, I already know this half right here is 10. Well, x plus 4, that would be 7, okay? So I'm going to redraw my right triangle here, guys, okay? I'm going to use the markings that it gave me here, okay? So over here on the side, all right, drawing my right triangle. Again, my center would be O. This piece would be W. This would be Z. There's my right angle. I already said ZW is 10. I already said OZ. We added x to 4. That gave us 7. So now we have to find our radius, which is OW, which would be our x here, okay? So this would be adding Pythagorean theorem, guys, all right? We're going to do the square root. So here x equals the square root of 7 squared plus 10 squared, all right? So we evaluate this. This is 49 plus 100, okay? We take the square root of 149. All right, I'll evaluate this in my calculator quickly. All right, so 49, we take the square root of that, what we end up with here, okay? Oh, I'm sorry, 149. Whoops, come on, coach. 149, I was about to say. All right, take the square root of that. All right, we get 12.2. So our radius here, the radius would be 12.2. All right, and it doesn't really say, so we'll just say units. It doesn't say inches or meters or anything like that. So the radius is 12.2 units. I know that is a multi-step problem, guys. We had to find the measures here, draw in a radius. This is a higher level problem. Again, solve for x, plugged it back in, and then we used Pythagorean theorem to find our radius that we drew in over here on the figure, okay? All right, guys, that's it for the notes today. Again, this is chapters 10.1, 10.2, and 10.3 over segments, lines, measures, and chords, all right? Again, go back and pause this at any point you need to and use this to do all your online assignments, all right? Thank you. Bye.